I'm going to be talking about functional programming on Android today. We've mostly seen object-oriented programming on Android, so it could be kind of strange to think about functional programming on Android. But we've seen an increase of the interest of it, especially with uses of the Kotlin programming language, libraries like RxJava, the model view intent, architecture, and things like that. But what does it really mean to write functional code, and how can that benefit us in Android? So I'm not going to be talking about like monads and category theory. That's for a different talk. I can point you to talks if you need to see these talks. They're great. Just not talking about them today. This talk came from my interest in functional programming and how it can be used on Android. I've started using it a little bit more and found it really beneficial. And it's also come from my hunger for diner food. So you'll see lots of diner food photos and examples. So this is as much of an exploration for me as it can be for anyone else. I don't have a functional programming background. I learned to program in Java. So this is geared towards if you're coming from an object-oriented background. So just a quick show of hands, who's familiar with the Kotlin programming language? Okay, Java, I'm sure, at least something similar to Java. And then RxJava at all? All right, cool. Most of my examples are in Kotlin, and I'll do my best to explain anything that might be unfamiliar in there, as well as with the RxJava that I use a little bit just because I like using it for concurrency. So who am I? I'll do a short little intro real quick. I'm Victoria Gonda. I work as an Android engineer at Buffer. We do social media apps, so social media management. And in fact, right now I'm using one of them to post the resources for this talk onto my Twitter while I talk. It's fun. We're a fully remote company. Feel free to visit the website or ask me lots of questions about it. I really enjoy working there. It's awesome. I'm also recently started as an author for Ray Wenderlich. It's a tutorial site. They're mostly known for their iOS and Swift tutorials. They're working on growing their Android and Kotlin tutorials, so I'm helping out with that. I'm based out of Chicago, and then I am also a dancer. I also wanted to give a quick shout out to Anoop. While doing my research for this talk, his blog post series was super helpful. I have them tweeted out. The title of it is Functional Programming for Android Developers. It's a really great series. If you're interested in this more after this talk, I encourage you to read them. So why we're here? Why functional programming? Like I said, we're seeing an increase of functional programming on Android with the use of Kotlin, RxJava. You have the option to use Arrow. And there's a lot of functional programming features that can be used to write clearer, more expressive code. The properties can also be used to help simplify concurrency. Concurrency can be a pain, and by using some of these properties, it can remove some of these pain points. Using functional programming can also make things easier to test, and we'll see a couple examples of this as well. So what is functional programming? It's not a tool or a library, really. It's more of it is a paradigm. It's a way of thinking about writing code, really a bunch of concepts. It came from lambda calculus and shows the way things are evaluated, often the same way that math expressions are evaluated. You'll see this a lot with the pure functions with no side effects that I'm going to talk about. Don't worry, we're not going to talk about the calculus stuff, just more about the concepts of functional programming. But I mean, math has proofs. Why shouldn't we have tests? So we can see then that it makes it easier to test if it's treated like math. So what are some of the concepts of functional programming? Functional programming is declarative. When you're writing code, you would like to focus more on what the computer should be doing rather than how. You're able to write faster that way. So by writing things in a more declarative way, focusing on the what, it makes your lives easier. You also want it to be explicit. You want it to be very clear what is happening, with minimizing the surprises that you may get. You don't want any surprises because some Boolean in another class was changed by something else that you didn't realize could happen. But I mean, it's there, it's changeable, anyone can. These kinds of things are what we're avoiding. We're also using constructs and data flow to avoid situations that can lead us into unexpected situations and unexpected states. Avoiding throwing errors, it will also fall into this category, and you'll see more of this later on. The fewer side effects, the more explicit the code, the better. Because of the characteristics of functional programming, it lends itself well to concurrency. We'll see how some of the properties help with this later on. Functional programming also has higher order functions, so functions can be treated as first class. You can pass a function into another function, passing logic around like that without having to enclose it in an instance of a class. Functional programming also has an emphasis on immutability. So once something is set or created, you can't change it. If you need something different, you have to create a new one. So here are the things that we're going to go over in this talk. We're going to see what pure functions are with no side effects and how this affects ordering. We're also going to go over how to make things immutable and how these things help when using them for concurrency. We're also going to go over higher order functions and functional error handling. So starting at the top, pure functions. Pure functions always give the same input, always give the same output given an input, and even if that's an empty input. So you have to pass in everything that's required for the operation to be performed. If you're doing addition, you need to pass in both numbers to be added, a 1 and a 2 in order to get a 3. It can't get that 2 from someplace else. And every time you pass in a 1 and a 2, you're going to get a 3. It also has no side effects, which we'll talk about after this. So there's no independence, or there's no dependence on the outside world. Because it's only the inputs and the outputs, this also makes it easy to test because you don't have to worry about setting up the context outside of it. You're only worried about the function. So let's look at a fun example. Let's look at making a milkshake. So you might have a blender and you add the milk and the ice cream and some chocolate syrup to get a chocolate milkshake. You want a chocolate milkshake, not get a surprise and get a chocolate banana, even if that might be really good. And then when you add maybe strawberry syrup instead of chocolate, you want a strawberry milkshake. You want this to be predictable. So here's a function. Let's see if this is pure. This is a blender function to make a milkshake. We pass in some ingredients, so maybe chocolate syrup. And then we get the milk, get the ice cream, then we have the ingredients, like our syrup, and we make our milkshake, and we return it. But it's getting the milk and the ice cream from outside the function. What if someone goes and swaps out that ice cream for chocolate ice cream and we were expecting vanilla ice cream? So our function is not solely dependent on its inputs, and it could have a different output given the same inputs. So this is not a pure function. Let's see if we can make it pure. Now everything is passed in as a parameter. So we're passing in our milk and our ice cream and our ingredients. Now it's not reliant on outside variables. We can be more confident that the function will behave in the way that we might expect. There's no way some other part of the code is going to change the ice cream on us now. And we can avoid that unexpected bug of getting the wrong kind of milkshake. Because of this change, it's also easier to test now. Before, we would have had to set up the outside world, make sure the milk and the ice cream were set before we were able to test the function. Now we can just call the function with the inputs, test the outputs, we're done. No extra context needed. So what about the side effects? Similar to not depending on outside variables, we're also not going to change anything on the outside. This could include changing a variable, writing to a file or the database. It could also be throwing an error. Because it doesn't change anything outside the context, it lessens the dependence on the outside world. When you have side effects in your code, it can also make it more difficult to read. You need to understand a greater context in order to understand the function. In addition to just looking at the code in the function, you also have to understand what fields are there, what they mean, what other things could be changing those fields. And it just takes more effort to be able to understand a function when you come across it. If you think about this in the math sense, adding 1 and 2 doesn't change the result of 3 plus 5 in another place. It's all self-contained. So let's picture our milkshake function again. What if the function also needed a glass to put the milkshake in? And it changed the number of glasses on the shelf because of that. So let's see if this would be avoiding side effects. So here's our blend function again. It's taking a glass from a list of glasses or a stack of glasses. I know you can't stack glasses all that well, or at least not high, but we're using a stack to store them. And so that's changing the number of glasses in this stack outside of the function. So that's clearly a side effect. What if another part of the code was depending on that glass to be there to make a root beer float, and now you have an error because there's no glasses left? This could cause an unexpected error, and we want to avoid that. Instead, let's pass in the glass. We want to pass in everything that's required as an input so that we can have the same output. This way we know it's safe, and we won't get into an unexpected situation. It's a pure function with no side effects. Now, think of the test that might have been written for it. We don't have to worry about populating that stack before our test. We just include the glasses, the inputs, test the output, and that's all we need to worry about. Now, I realize that sometimes side effects can be unavoidable. What would our programs be without having to write to files or databases and retrieving that stuff later? But the idea with this on Android is that you push those side effects to the edges of your program so that as much of your code can only focus on the logic, self-contained methods as possible, so that the parts of your code that aren't relying on those side effects can be more consistent, more easily testable, and just don't have to rely on those things. It will help minimize surprises in those parts of the code and bring clarity to your code. So the main idea there is to isolate those side effects so other parts of your code don't have to worry about them. When we have pure functions that only depend on input and don't change the state of the world, order stops mattering. Pure functions can be executed in any order, assuming the input of one or the output of one isn't the input of another. If you don't have to worry about the order of things, you could also do them, say, at the same time. So yay, concurrency. Like I said before, if you add 1 and 2 over here, it doesn't change 3 plus 5 over here. You can do them at the same time, or one of them first and one of them second. So let's picture this example and see how it can change if we have pure functions or not. Let's do making toast, mixing eggs to make, and frying bacon. Now, these should be pretty independent of each other, right? So we should be able to do them in any order or at the same time. Let's take a look at one of these functions. So here's one of these functions, specifically the one to make toast. But notice that it is relying on something on the outside of the input. It's grabbing a cook from a global pool of cooks. Turns out all three of those functions are doing that. But that's OK. We think like all the cooks will be in the same order in the right spot all the time. It'll be fine. But what if one of the cooks is homesick that day and there's not enough hands? Or what if the wrong cook gets pulled in to make the wrong thing? Like, we don't want the toast burner making the toast. So we think that it might be the same all of the time, but we really don't know. Other things have access to this. So let's see how we can avoid these unexpected behaviors. We can change our function to make them pure. Now our cooks will be passed in as a parameter. We always know that we have the cook that we need to get the job done. Because this is now a pure function, this means that they can be called in any order or at the same time. Now that we have 3 cooks, we know that we're going to have a cook in each of those functions. We can get things done concurrently, since we know none of the functions rely on any of the others. And then to bring it back to testing, as easy it was to test pure functions, we can test the interactions of these much easier because we don't have to worry about testing any order. We just test inputs and outputs. No extravagant setup for that. Next, let's look at immutability. So not changing things. If we want something that's different, we need to create a new one. Once something's created, it can't be changed. Just like if you have a 4, it's not going to magically turn into a 5, or you can't force it to turn into a 5. You can have a 5 as a result of 4 plus 1, but you can't just change a 4 to a 5. Same thing here. So revisiting our diner, how strange would it be if somewhere between the griddle and the table, a veggie burger turned into a beef burger? That really wouldn't be right, and it would be unexpected. We're trying to avoid these unexpected things. Let's see how we can avoid that. When we're doing this, we also have to watch for mutable child objects or nested objects, and we'll go over how we can look out for these in this section. OK, so here's our burger. We have, it's a class burger, and then one property type. So that's where we'll say what type of burger it is. It's a string, as it says string, and then we're using a var. If you're not familiar with Kotlin, this makes this a mutable property. Just to give you a little bit more context, I'll show you the equivalent in Java. So we have our burger, we have a field with the type string field. And then we're setting that type in the constructor. And then we have a getter and a setter for that type. This setter is what really makes the difference in this case. After we make our burger, we can then still change it, the type. Imagine the unexpected behavior we can get from this, like getting the wrong burger delivered to your table. Let's make this immutable so that we can avoid that unexpected behavior. In Kotlin, all we have to do is make this a val instead of a var. So that makes it a final property. Strings are immutable, so we don't have to worry about the string object itself changing. To understand this with the Java example, here it is. It made the field final, so once it's set, it can't be changed. And then we've also removed the setter for the field, so we can only access it. The class is also final, so we can't extend it and modify it and cause wacky things with that. We didn't make any changes to make the Kotlin class final because Kotlin classes are final by default. Now, if we try to modify the type, we won't be able to. If we want a beef burger, we'll just have to make a new one. Now, Kotlin has smart casting. It pays attention to if something is mutable and could be changed, even if it's on a different thread. Let's take a look at if the type is mutable again. Here we also have it nullable. That's why you see this question mark after string. Nullability is built into the type system for Kotlin. So the type stores if something can be null or not. So we have our class with a nullable, mutable type on our burger. We're checking if type is null, and then we're getting the length for it for some reason. I don't know, but we're getting the length. And we have a compiler error there because the type could be null. Sure, we're calling it right after the if statement, but it's still possible that the type could be changed to null on another thread. And Kotlin knows this because it's mutable. Unlikely, but it definitely could happen. We've seen those weird concurrency bugs that are so much fun to debug. So how does this change if we make the type immutable? So we're changing it back to a val. So now we have our val type. It's still nullable. We still have that question mark there. But now after we check if the type is null, we're safe to call things on it. Because it's immutable, we know that it can't change. And Kotlin knows this too. This is great. We can see the wonders that using immutability can do in preventing unexpected behavior, especially with concurrency. There's still another thing we have to watch out for, like I mentioned before. We can't reassign a property, but if the object itself is mutable, it could still change. We have to watch out for that. So imagine we have an additional property on our burger, toppings. No, we can't assign a new list to it. But if the list is mutable, like default lists in Java, the items in the list can change. And that would be violating immutability. And this could also lead to unexpected behavior. This would be the same as, like, I don't know, maybe changing a matrix in math, but without performing any operations on it. It's just a different matrix now, which would be weird in math, so we're not going to do that here. So in this example, we can change the items of the topping list, even though we can't reassign the list. So for this, it looks like this customer is getting onions on their burger, whether they wanted them or not. We want our burgers to be predictable. So how do we do that? In Kotlin, it's pretty easy. Kotlin has both mutable and immutable list types, with the default being immutable. This just means that there's no mutating methods on the list. You can't add anything or subtract or remove anything after the list is created. Easy enough. If the list had mutable contents, we'd have to do something about that too. Either make the objects in the list immutable or create copies of them whenever they're requested. But because we're using strings here, which is immutable, we're fine. We have to be a little bit careful with this in Kotlin, especially if you're interacting with Java, because underneath at the bytecode level, it's using the same mutable list as Java. So just watch out for that. If you decide to do this, you're expecting it to be immutable, but you're using it in Java, and it's mutable there. To make this safe with Java, we have to make a copy of the list whenever it's requested. This will ensure that if the person retrieving it tries to change anything on the list, it's not going to change the burger itself. And the same thing here with if the objects stored in the list were mutable, we'd either have to make those items immutable or recurse down the items and make sure the items in the list are copied as well. Now, the user isn't going to get the onions that they didn't ask for. There are a couple other options in Java. If you're trying to use immutable lists, you could wrap the list to get rid of any mutating methods, or use a library that has immutable collections. All right, so concurrency, always fun. By using the properties that we've talked about so far, it can make concurrency easier. Using pure functions with no side effects helps eliminate some of the unexpected behavior and those bugs that we can get, those concurrency bugs. Like I said before, when two equations are evaluated at the same time, at different times, it's not going to change the result of the other. So keeping up with our burger example, if we make one burger, it shouldn't change the toppings of another burger. When someone orders a burger with tomato and another with lettuce, they should each get what they ask for, not a burger with tomato and lettuce. So imagine we have both of these orders. We get the toppings for one and then the other, but they end up on the same burger. That would not be great. Talk about unexpected. So let's see, how can this go wrong? We have a function that adds toppings to our burger and emits it as, it's returning an observable that emits it in a stream. So kind of sending it out, sending it down the pipeline in the diner. Notice we're using our mutable version of the burger, and we're adding toppings to the burger that's passed in. I don't know if you spotted what's going to go wrong with this yet. So now we have a busy kitchen, and we want to take advantage of working on things in parallel so that we can prep everything quicker. We have multiple cooks. They should all be working at the same time. We're going to use RxJava for this. I'll walk through what this is doing. But I like using RxJava for using different threads and schedulers. It simplifies things. So if you're not familiar with RxJava, what we have here is we're calling add toppings twice and getting two different streams from that. They're both like on a kitchen scheduler thread. And then we're merging them together. So you can kind of think of this as putting them on the window for one person to take out and deliver. We can't guarantee the order of them. We don't know when each burger will be done. We just know they'll be there at some point to deliver to the table. They're going to be each prepared on their own, we'll call it a kitchen thread. This might be an IO thread or a worker thread in your program. And then after that, we're observing on the delivery thread. So we're going to say that in the end, when they're emitted, when the burgers are done, they'll be delivered on this different delivery thread. And the subscribe is just listening for those events and delivering them. So that's what the merge, observe on, subscribe, deliver, that's what that's doing. So I don't know if you spotted this, but we're passing in the same burger to both of those lists because they both wanted veggie burgers. We're going to pass in a veggie burger to both of them. But add toppings is mutating that same burger. So depending on the order, it's going to take the burger, add tomato, send it out, take the same burger, add lettuce, so now it also has tomato and lettuce. This is unexpected. This is not what we want. So how does this change if we use our immutable version of our burger, making it a pure function? Let's see how we can change that. So like I said before, the add toppings, each time we called it, each on different threads, we're modifying the same burger. Here, we're now using our immutable burger. And in order to add the toppings, we have to make a copy of it. So it's emitting a different instance of our burger. With this change, there will be, for sure, 2 different burgers, and each person is going to get the burger that they ordered. It removes our unexpected behavior and our pains with the concurrency here without using any sort of locks. So now, higher order functions. With higher order functions, functions are first class, and we can pass them into other functions. There's a number of places that this could be helpful. The classic example, at least in Android, is an on-click listener. In Java, you'd have to create an on-click listener class with one function, click, and then you can put your logic in and pass it in to set the listener. By using functions, you're able to just pass in the logic that would be in your click function, removing all of that extra ceremony of creating the class around it. Another time that I found this really helpful is if you have some logic and the beginning part's always the same and the end part is always the same, but the middle changes. Kind of like hamburgering that. And you don't really want to duplicate the beginning and the end, but you kind of have to because the middle changes. You can avoid that by using higher order functions, passing in just the logic for that middle part into the function. We're going to look at an example for each of these cases. First, when the beginning and the end are the same, but the middle parts are different. This could be like writing to shared preferences in Android. You have to get them, open them, write to them. What you write is going to be different each time. And then you have to commit or apply. In this, we're going to take the series to cook potatoes. We're always going to wash and peel the potatoes, and we're always going to eat them in the end. But how we cook them might change. So we're going to pass that logic in as a function. So here we have a function to make these potatoes. We're passing in some potatoes, and then we're going to pass in the function to say how we want to cook the potatoes. In Kotlin, to say that we want to pass in a function, we name the input variable. We say the input type, in parentheses, potatoes. Then we have an arrow, and then the return type. So then in our body, we're washing and peeling the potatoes. We're calling the function that was passed in to cook them however we want. And then we eat the potatoes. And then to call it, maybe we'll fry the potatoes, maybe we're making French fries. To call the function, we just contain this logic in curly braces, and we can pass it in without having any additional ceremony of wrapping it in an instance of an object. We're just saying, make some potatoes by frying them. If you're familiar with Kotlin, you might realize that this is a little bit of a verbose way to call it. Just wanted to make sure this is probably the easiest way to understand if you're coming from Java and you don't have experience with a similar syntax. Because there's only one input variable, we don't have to name it potatoes. We can let it default to a variable named it. So it is the same thing as potatoes was above. Because the function, or lambda being passed in, is the last parameter of the function, we can put the curly braces outside of the parentheses. And then because there's 0 or 1 inputs to it, we can use this function reference. So just like that, we have a function to make and eat any kind of potato without including the repetition of the prep and the eat work. We can cook them any way we want. It's great. So just look at the power that this gives us. All right, time to look at the other case for passing in a bit of logic without having to create a whole new class for it. So instead of an on-click listener, here we'll do an on-finished-eating listener. So we're going to listen for when the customer is done eating, and then we're going to bring them their check and clear the dishes. So with these, Usually it's responding to an event, like a button click, or maybe something being emitted in an RX stream like we saw before. So here's our listener. We don't have to create a unfinished eating listener anonymous class instance with our logic in this method. We're just passing in just the logic that we need. And it's so much cleaner, and you avoid all of that ceremony. All right. Next, we're going to look at error handling. This is the last property that we're going to look at in this. So in functional programming, if you haven't noticed yet, everything is either a value or a computation, an evaluation. This helps us to avoid unexpected states. And with error handling, we also want to avoid those unexpected states. We don't want something getting thrown somewhere and us not catching it because it's unexpected. So in functional programming, errors are treated as values. So we have our deliver burger method. We've seen this before. But what if this could cause an error? What if when it's being delivered, the plate gets dropped? We could surround it in a try catch if we know this can happen. Sure, and then we can make a new burger. But that's not a very functional way to do it. And it can lead to unexpected states. It also can be difficult when you have more things that you need to do. If we catch a dropped plate exception, which one threw that error? We don't really know. So what do we do then? We could also wrap each and every one in a try catch, which is fine, but that doesn't really look very nice. It's not very fun. So in functional programming, we want to treat the error as a piece of data. We don't want to throw an error. We want to return an error as a piece of data. This can be done by returning a sort of result. This result has a success on it. It's just a Boolean to say if delivering it was successful. There's a bunch of different ways that you can do this. If you use nullability, you can check to see if something's null. Here, we're just going to use a success Boolean. So we can check it and make a new burger if we want. We could even ignore the result if you don't care. This might be the case in if you've ever had something throw something, you don't really care if error or not, so then you just have an empty catch block. Then here we can just omit that if statement and not care. Just to show we can also inline this, just if it was success, or if it was not a success, make a new burger. I've also seen this where the result object has an error on it, like maybe a string, or you have an error class that you use. So that's how you do error handling with functional programming, treating an error just as any other type of data. So here are some tools that you can use to do functional programming on Android, as well as other places as well, especially in the Java ecosystem. We saw a lot today, the Kotlin programming language. It works on the Java virtual machine. It has higher order functions like we saw and defaults towards immutability. It's really great. In my preference when working with the Java ecosystem, they also have options for JavaScript and native, if that's where you're working and you're still interested in trying out Kotlin. There's also RxJava, which we saw a bit of it. It's really helpful for doing concurrency cleanly. It uses a declarative style, especially when working with collections and threads. It also makes it easy to avoid side effects. It doesn't inherently change the code. You have to change the context. Like you have to specifically do that. And then Arrow, I haven't personally worked with it yet, but I've heard some great things about it. It's a library for typed functional programming in Kotlin. So if you're looking for some more of that pure functional programming with monads and such in the functional programming lingo that I forgot after I graduated, Arrow will make you really happy. I can point you to some things if you're interested in checking it out. And then I've also seen functional programming successful with the model view intent architecture on Android. So let's look at a real-life example from the buffer code base, because Diner Food's great, but what use is fun examples if you can't use it in real life? So here is an example of a Lambda that we're passing into a higher order function, specifically an RxJava stream. And it follows all of the things that we've talked about. This comes from a view model. We're using a reactive model view intent / clean architecture architect for our app. So this is from the view model. It's mapping some result to the UI model that should be displayed. Before even digging in, we see it's a higher order function. So just quick what it's doing so we understand the context. Within it, we're seeing what type the result is to help determine the state that we should return. So if it's a get last state, we're returning the previous state. If it's a load folders task, we do a little bit of other logic to find out what we need to return. If the status is in flight, we're going to do an in progress UI model, so it can show like the little loading spinner. And then notice that we have, if the task status is a failure, see just data, we're going to do a failed UI model, so show an error message. We can see how simple that is to just treat the error like a piece of data and along with everything else next to it. This is a pure function. It always gives us the same output given an input. So every time we get a load folders task with a status of success, we're going to get a folders UI model, folders loaded, and they're both going to have the same immutable list of folders with them. It also has no side effects, so we're not throwing anything, we're not assigning some variable, we're not writing to the database, just inputs and outputs. Because it's independent of the outside world, only dependent on inputs and outputs, it can be called in any order alongside other functions. Like I said, this is part of a RxJava stream. It's running concurrently along with other things. Also, you can't see directly from this snippet, but the folders UI models, those different ones, are all immutable, as well as the result, the folders results, those different kinds there, which provides additional safety, as we saw that immutability can do. Those folders aren't about to change between when we get the result and when we're displaying them. And then, like I pointed out, we're also handling errors in a functional programming way. Additionally, avoiding those unexpected states. So here are some resources. I also have them tweeted out. You can find my Twitter at @ttgonda. The top resource here is the one that I mentioned at the beginning, functional programming for Android developers. Some other neat ones that would be fun to look at is if you're interested in RxJava, you could look at the functional reactive programming with RxJava. And then if you're interested in learning more about Arrow, there's a course on Castor.io, functional programming in Kotlin with Arrow. You can reference these slides again. They're on my Twitter. They're also on SpeakerDeck. And now I'd like to thank you all for coming and open it up for discussion. I'm happy to answer any questions, but I think with a group this size, it can be a discussion. So yeah, thank you.